Potential energy. Basically, potential energy is related to the height. Now, important information regarding the gravitational potential energy. First, important information. The gravitational potential energy of a body on the surface of Earth is zero. So, first we are considering the gravitational potential energy. Gravitational potential energy on the surface of Earth is zero. Second one, gravitational potential energy of a body increases if the body moves upward. Height increases, then potential energy increases. Third point, gravitational potential energy of a body decreases when you move downwards. So if height decreases, potential energy decreases. Fourth point, gravitational potential energy depends only on the initial and final position of the body and not on the path followed by the body to go from initial position to the final position. So gravitational potential energy depends only initial and final position. So these are some points related to gravitational potential energy. Now, interconversion of potential energy into the kinetic energy. How to convert the potential energy into kinetic energy? It's mathematical proof. Let us see here. So interconversion of potential energy and kinetic energy Let us consider at the height h, the potential energy is mgh and the kinetic energy is 0. So, and at the lowest point, when the object is dropped, at the lowest point the potential energy is 0 and kinetic energy is your maximum, half mv square, and in between that the sum of energy is constant. Let us how to convert the kinetic energy into potential energy. We apply the motion equation, third equation. We'll apply the motion third equation. What is v square is equal to u square plus twice gh in the downward direction. V square is equal to u square plus twice gh, and as we know, when the object is dropped, its initial velocity is 0, so v square is equal to twice gh. So the potential energy and kinetic energy is converted by this formula. Suppose kinetic energy is half mv square is given at the bottom, and when we apply the v square is equal to twice gh, so half m twice gh, 2 and 2 cancel out, will get kinetic energy is equal to mgh. It means what? At any point the maximum kinetic energy is equal to maximum potential energy. At any other topmost point maximum potential energy and the bottom point maximum kinetic energy, both are equal to each other. So it shows the laws of conservation of energy. Law of conservation of energy. According to this law, the total sum of energy of all the kinds of in an isolated system remains constant at all times. It means that energy can neither be created nor be destroyed, energy can only be transferred from one form to the another form. So total sum of energy is constant. It means we can say at any point kinetic energy plus potential energy is equal to constant, or we can say at any point k1 plus u1 is equal to at any other point k2 plus u2, where k1 u1 is initial kinetic potential energy and k2 or u2 is your final kinetic and potential energy, and the sum of this also known as mechanical energy. So what is the mechanical energy? Is the addition of the kinetic energy plus potential energy. Mechanical energy, that is the addition of kinetic energy plus potential energy at any point, so is equal to kinetic energy plus potential energy. And when we draw a diagram between the position and the kinetic energy, potential energy, so this will be your graph between the position and different types of energies. First, kinetic energy. So initially at the highest point the kinetic energy is 0, and as we moves upward in the graph, it means the particle is moving towards the downwards, the velocity is increases, so kinetic energy is increasing. Similarly, the opposite phenomena is happening with the potential energy. So at the topmost point the potential energy is maximum and it is reduces as we move towards the downwards direction. So addition of these two energy at any point, is represent the total energy. This green line represents the total energy. It is all total energy.
Or we say mechanical energy. So it is always constant. Now, work energy theorem.
This theorem states that the work done by all the forces acting on a body is equal to the change in kinetic energy of the body. That means what? Work done by all the forces acting on a body is equal to the change in kinetic energy of the body. The change in kinetic energy of the body. We can conclude here this work energy theorem. As we know, work done is equal to force into displacement. Work done is equal to force into displacement F into S in a straight line motion if we are considering. And also we know force is equal to mass into acceleration into S. So we know the equation of motion V square is equal to U square plus twice AS, and we can put here V square minus u square upon 2 is equal to A into S. So in equation of work done, when we put here W is equal to, in place of A into S, we can put V square minus U square upon 2. So M into V square minus U square upon 2, and this you can say it is what, when we multiply by the M, will get half M V square minus half M U square. So where the half M V square is your final kinetic energy, half mv square your final kinetic energy,
minus half mv square your initial kinetic energy. Therefore, work done is equal to what? Change in kinetic energy represent change is what? Delta Ke. So this is known as work energy theorem. So work is converted into the kinetic energy. Whatever the change in energy, if velocity increases, then work is done on the system, and if velocity decreases, work is done by the system. So these two case we have discussed. Understanding better.
a
body of mass 10 kg, example, a body of mass 10 kg is kept at a height h 10 meter from the ground when it is released after some time. Its kinetic energy becomes 450 joule. So when it is released after some time, its kinetic energy is 450 joule. What will be the potential energy of the body at that instant? So we have to find out the potential energy at that instant, where the kinetic energy is 450 joule. So as we know energy theorems, the initial energy, total potential energy is, as we know, the total energy is definitely initial energy, and it is what? mgh. This is your total energy. 10 is your mass, g is let us take 10, and h is your height is 10. So the 1000 joule is your total energy, and at any instant, as we know, total energy is the sum of the potential energy plus kinetic energy at any point. So total energy is 1000 joule are given, potential kinetic energy is also given at that instance 450 joule. We have to find the potential energy. So potential energy will be equal to 1000 minus 450 joule. So we'll get it, what is 550 joule is your potential energy. Okay, so this is the example of work energy theorems, and total energy is constant. Some other example of conservation of energy. First, vibration of simple pendulum.
Vibration of simple pendulum.
In the simple pendulum,
it is the mean position, and when we take one side,
it will oscillate by this path. Now, so when the velocity of this bob is 0, we say maximum potential energy. So this point at which velocities are 0, we say maximum potential energy. And similarly, at which the velocities are maximum, we say maximum kinetic energy. So this point is maximum kinetic energy. Now, so it shows the total energy is always conserved at any instant. If you discuss at any instant, suppose this is the point at any instant, if you discuss, so here the total energy is always conserved is the sum of kinetic energy at that instant plus potential energy at that instant, and it should be equal to either maximum kinetic energy or maximum potential energy. Similarly, there are many examples. Motion of a small spherical ball over a watch glass. And now let us start with the power. So power, we have learned that when a force causes displacement, work is done. Work is done is measured as the product of the magnitude of force and the displacement in its direction. A certain amount of work done appears to be trying if done quickly and in a very short time. It means time is considerable in the power. Same amount of work is done slowly in a larger interval of time gives no feeling of tiredness. So the power is considered with the time. How? In this fact has given rise to a new concept, that is rate of at which the work is done, and it is defined the power. So definition of the power is what? Rate of doing work, rate of doing work, it means work done per unit time by a man or a machine is called power of the man or the machine. It is represented by the symbol P and it is a scalar quantity. So expression of the power, how to calculate? Power is equal to work upon time.
And also we know, we can convert this into the other forms. Work done is equal to was F vector dot S vector upon time equal to
F vector dot S vector upon time t, or power is equal to, we say, F vector dot V vector.
So these are the formula of the power. Unit of the power is watt. So we can make a relation with 1 watt is equal to 1 joule per second. And also we can take unit of the power in another form, like 1 kilowatt is equal to 10 to the power 3 watt. Similarly 1 megawatt, it means 10 to the power 6 watt. 1 gigawatt, it means 10 to the power 9 watt. One commercial unit of the power is horsepower. So 1 horsepower is equal to 746 watt.